Hello AMU students, we are Andrea Lima and Ronald Ursek, and I want to introduce our heat transfer project, the effect of gap distance between double pane windows. We believe that all of us who live in Rexburg understand the importance of double pane windows to keep our house insulated during the winter or summertime, and consequently help us to reduce energy costs. The space between the panes are usually filled with air, but can also be filled with other type of gases, like argon. Argon is a better insulator than air because of its lower thermal conductivity. Despite its lower thermal conductivity, to seal your window with argon, it is a bit more expensive, and you eventually will lose the argon because of leaks from cracks created by the expansion and contraction of the window seals due to temperature changes. So, we thought that a better way to manage the insulation efficiency of the air could be managing the gap distance between the window panes. And the objective of this project is to evaluate the effects of the gap distance between window panes and if the change in distance would considerably impact the room temperature. To perform this experiment, we used the following equipment: cardboard box, insulating material, Arduino Uno R3, 2 DHT sensors, an infrared thermometer, thermocouples, 2 glass panes, and a heat gun. The cardboard was well insulated, and the glass panes were set up first at 4 centimeters distance from each other, and then 8 centimeters far from each other. Then the heat gun blew hot air in the front pane by impinging air jet at 5.6 meters per second. The infrared gave us the temperature of the outer surface of the glass, which is the same as the ambient temperature. A thermocouple attached to the inside surface gave us the inner surface temperature of this glass. This temperature sensor gave us the temperature in the gap. A second and a third thermocouple gave us the surface temperatures of the second glass. This second DHT sensor gave us the temperature in the room. It's important to observe that if the box was closed at the end, it would be a more complex experiment because of the transient conduction. To avoid this complexity, the end of the room was removed, giving us a steady-state condition. And this is our experiment assembly. We took a screenshot of the Arduino serial monitor to show that steady-state conditions were achieved. This condition was achieved after about 8 and 9 minutes. By observing the data, we can see that temperatures are not changing with time, and the experimental results were very impressive. The results were beyond our expectations. By doubling the gap distance from 4 centimeters to 8 centimeters, the temperature dropped by a factor of 1.7, from a 49 degrees Celsius to a 29 degrees Celsius. Changing from a single pane to a double pane of 4 centimeters, the temperature dropped by a factor of 1.2. And switching from a single pane to a 8 centimeters double pane, the temperature dropped by a factor of 2, from a 59 degrees Celsius to a 29 degrees Celsius. We were not able to achieve the same ambient temperature when testing the 4 centimeters gap, but 3% off can be negligible. It is also very interesting to see that the gap temperature did not change. We need to perform some theoretical calculations in order to compare with our experimental data. The distance from the glass to the heat gun must follow certain conditions. These are based on impinging jet equations for one circular nozzle. That is found on Chapter 7.7 of Fundamentals of Heat and Mass Transfer. By meeting these conditions, then we can use Nusselt correlations for an impinging jet in order to find the heat transfer coefficient of the air blew by the heat gun. With this ambient heat transfer coefficient, we can then calculate the heat transfer. With the heat transfer, then we are able to calculate all of the temperatures. This figure shows the different types of heat transfer for this experiment. In order to use the proper equations, we need to identify the correct mode. First, observe that the radiation from the heat gun to the first glass was neglected. There is a forced convection caused by impinging jet in the first glass. and there is a conduction through the glass, and there is a free convection in the gap chamber. There is a conduction through the second glass, and then a free convection to the room. And these are our theoretical calculations. The heat transfer calculated was 198.2 watts. The heat gun power is 300 watts. Considering efficiency and the distance from the nozzle to the first glass, the result matches the experimental data. The heat transfer coefficients calculated from the Nusselt correlations are in the acceptable range for a free and a forced convection. The calculated temperatures are very incorrect. We have checked our calculations several times, but at this point, we were not able to identify what went wrong with the parameters or equations that we may be using to calculate temperatures. This is our experimental versus theoretical results. It is noticeable that not even a comparison were needed, but we want to provide you the total difference perspective. The experimental results were repeated, and the results achieved were the same. Our experimental and calculation approach was even considered valid from our instructor. In order to assist anyone who wants to replicate this experiment, it is important to inform some of the limitations. These limitations may be the reason that we have difference between the theoretical and the experimental data. We neglect the radiation from the heat gun and from the infrared thermometer. We also did not consider the resolution and uncertainty from the different electronics we use. The room where the experiment was performed had people circulating all the time, and we had ambient heater on. That may affect our readings and even result in an external convection scenario for the room, and not a free convection. The thermal conductivity for the glass changed according to the temperature. After some research, the only value for the glass that we utilized was the 300 Kelvin. As mentioned before, we had to look for assistance from our instructor because we were not able to achieve the same experimental temperatures. We conclude that a free convection equation may not be the best approach to calculate the temperatures in the gap and in the room. Our next approach is using equations from rectangular cavities. That is section 9.8.1 of Fundamental of Heat and Mass Transfer. At the same time, we request your opinion, ideas, and suggestions of sections, equations, and principles that we should consider in our next approach to calculate these internal temperatures. Our calculations were done using resistance method, and seems that our area is so small that is giving us very high values for the convection resistance. If we just consider conduction resistance, we achieve exactly the same temperature that we got from the experiment. We appreciate your feedback. Thanks for watching.